Let us next see operations on ideals. Let's start our discussion by considering two ideals in a ring. Let I and j be two ideals in the ring A. Then the sum of I and j is defined as this. Okay, so I plus j is the set of all elements of this form A plus B, where A is coming from I and B is coming from j. Then I plus j is also an ideal of A. And in fact, we have already seen this, we have proved this fact in Herstein's topics in algebra. Specifically here, see exercise 5 of section 3-4. Of Herstein's topics in algebra. In fact, this I plus j turns out to be the smallest ideal containing I and j. Let's see how that is true. Okay, let us establish this fact. Clearly, I plus j contains both I and j. How? You see, you can take, for example, b equal to 0 because 0 is available in j. So in that way, you get all the elements of I as elements of I plus j, and that is why I plus j contains I as a subset. Similarly, by choosing a equal to 0, you get all the elements of j as elements in I plus j. So that way, I plus j also contains j. Fine. So I plus j is an ideal containing both I and j. But why is it the smallest ideal? Let K be any ideal of A such that K contains both I and j. Our aim now is to prove that K also contains I plus j. So for that, we are going to choose any element of I plus j and will show that it also belongs to K, which actually you can maybe see, it's almost obvious. Let A belong to I and B belong to j. Then A and B both belong to K because of these containments. Thus, A plus B also belongs to K. However, A plus B is any arbitrary element of I plus j, So I plus j is contained in K. In other words, any ideal K of our ring which contains both I and j also contains I plus j. So in that sense, I plus j is the smallest ideal containing both I and j. Now this of course can be generalized. This entire thing can be generalized like this. In general, let I be any family of ideals of A, where you can understand that this is an indexed family of ideals of A, where for each I belonging to this indexed set S, I is an ideal of A. Now this family may be infinite, okay, that's not a problem. We then define the sum of the ideals in this family to be the set of all elements, or we can write sums where xi belongs to I for each I belonging to S, and there is another condition, and xi is not equal to 0 for at most finitely many indices I in S. This last part, this last condition ensures that we are not dealing with any infinite sum, because the moment we have infinite sum, then there comes the question of convergence. So we don't need those things. That is why, so what is this? This is the set of all such sums in which actually at most finitely many xi's are there. Okay. So the set of these sums forms an ideal, and that is defined to be the sum of these ideals. We denote to by the way, to verify that this set is an ideal, you can proceed just like this, just like how you show that I plus j is an ideal. It's essentially the same. We denote this ideal by this symbol I. If you want, you can write the variation of I, or if you can, if you know, I mean, if it's understood what S is and where I is varying, you can just simply write summation II. That will also mean the same thing. And just like this one is the smallest ideal containing both I and j, this is the smallest ideal containing all these i's. And that fact also can be established just like how we did for I plus j. Summation this is the smallest ideal of A containing I for every I belonging to S. Okay, so that is the sum of ideals. First for two ideals and then the general one. Next we come to an even easier case, actually, which we already know. For a non-empty family. So again we are considering a family of ideals. Of ideals of A, their intersection is also an ideal of A. We want the family to be non-empty. This essentially means that S is a non-empty index set, because otherwise there is a logical problem in defining intersection. Okay, for that we need non-emptiness. So this is a fact we already know, and in fact we know this fact in this generality, in this general form. And because of this, the ideals of A form a complete lattice. To see how you consider, let S be, we have already taken S here, so let me just denote it by something else. Let T be the set of all ideals of A. This is a partially ordered set, and this partially ordered set will be a complete lattice provided every subset has a join and a meet. And in this case, really, there are different subsets of T that you can choose. The empty set is also one. For the subset this of T, 0 is the meet and the entire ring is the join. Okay, 0 means the 0 ideal, and the entire ring of course is also an ideal. So these are elements of T, and the first one acts as the meet of the empty set and the second one acts as its join. And for a non-empty subset of T, say U, the meet is the intersection of all the elements in U, I, where I belongs to U, and the join is the sum of all the ideals in U. Yeah. And that is why this is a complete lattice. Let I and J be two ideals of A. then their product ij is the ideal generated by elements of the form x, y, where x belongs to I and y belongs to j. Ij is the ideal generated by the subset, this subset of A. So you recall what ideal generated by a subset means. It means that it is the intersection of all ideals of A which contain this subset as a subset inside of them. Okay, so it's that thing. So we already know that such an intersection is an ideal and is the in fact the smallest ideal containing this subset. And for this specific subset, the ideal that we get is Ij. The elements of Ij are of the form summation xi yi, where xi belongs to I, yi belongs to j, and the sum is finite. Now this entire fact, the product of two ideals, how it is defined and what its elements look like, these are nothing new to us. We have already done this again in Herstein's topics in algebra. In this exercise, see exercise 6 of same section as that one, 3, 4 of Herstein. And just like we considered the general version of sum of ideals, here also we can consider the general version of product of ideals. But unlike sum, where infinitely many ideals were taken, I mean that possibility is there, here we can take only finitely many ideals. Finite family of ideals, say I1, I2, In, we define their product to be ideal generated by this set x1, x2 generated by elements of this form. You can clearly see here that xi needs to come from ii. You can clearly see that this is a direct generalization of that two ideal case. In particular, all these ideals are the same ideal, then we have this power of that ideal I, which of course its definition comes from here. So this is the special case of this. By convention, okay, you understand here that n is a positive integer. However, by convention we define for any ideal I of our ring this, okay, which is just the entire ring. So if you go back to this definition of the generating set of our product ideal, in this case, this is the ideal generated by, again, such products where all the xi's come from that one single I. So these are three basic operations on ideals. We are going to see more operations as we gradually go deeper and deeper into the subject. After this, there are some examples that we will see next week. So that will be all for today. See you tomorrow with a new upload. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.